In this video, we'll talk about connected and disconnected graphs. We'll introduce the term component, and we'll prove 3 sufficient conditions for a graph to be connected based on their non-adjacent degree sum, minimum degree, and size. So first, what's a connected graph? Well, we say two vertices in a graph are connected if there's some UV path between them. So two vertices U and V in a graph are connected if G contains a UV path. So there's some path between them. A graph is connected if every 2 vertices are connected. So we could say a graph is connected if between any 2 vertices U and V, there's some UV path. So for instance, G would be a connected graph because between any 2 vertices I can find some path. H here would not be a connected graph because there exist 2 vertices, namely, let's say this one and this one, of which there is no path between them. So H is disconnected. Now when we have a disconnected graph, we can talk about the number of components, and that's denoted with a K. So here there are, pretty intuitive, there's 2 components to this. But what exactly is a component? We say K of H equals to 2, so usually K of a graph is the number of components. A component is a maximal connected subgraph. So that is, it's a subgraph that's not a proper subgraph of any connected subgraph of the graph. So it's the number of, just think of them like connected components. Clearly here, the number of components is 2. And here, for a connected graph, the number of components is necessarily 1. So that's connected and disconnected. Now, how do we know if a graph is connected or not? Well, one, we could draw it and just look at it, but what if it's really big? What if we don't have a drawing of it? How can we know if a graph is connected just by knowing how many edges are in it or what the minimum degree is, things like this. For instance, we know that a complete graph is connected and that has minimum degree n minus 1. Complete graph of order n has minimum degree n minus 1, and that's connected. So the question would be, how many edges do you have to remove from the graph or from a particular vertex to end up with a disconnected graph? So this is the idea, is there's some threshold for the minimum degree of a graph, such that if it's higher than that threshold, it's necessarily connected, and if it's lower than that threshold, we can find some disconnected graph. So this is the nature of these 3 theorems we get in this section. So theorem 2.3. So this isn't quite about minimum degree. We'll see a corollary that follows from this about minimum degree. But this says that if we have a non-trivial graph of order n, such that for every 2 vertices, every 2 non-adjacent vertices, non-adjacent vertices, U and V, then G is connected. So we call this degree of U plus degree of V for 2 non-adjacent vertices. This is a non-adjacent degree sum of the graph, and what this is saying is, so any 2 non-adjacent vertices, pick them out, add up their degrees. If that's greater than or equal to n minus 1 for any pair like that, then the graph is necessarily connected. And so this is a rather useful theorem. Let's see why this is true. So let's look at a proof of this. Okay, so right. So let x and y be any 2 vertices of G, and I want to show the graph is connected. So I want to show there's some xy path. Any 2 vertices of G. Want to show, I'll just say we show there is an xy path, and then the graph will be connected. So first off, if x and y, if x and y are adjacent, so if x, y is an edge, then obviously there's an xy path, right? Just the edge xy. Edge, then the result is immediate. So nothing to show there if they're adjacent. So assume x, y is not an edge. So in particular, these x and y are not adjacent, and so by assumption, degree of x plus degree of y is greater than or equal to n minus 1. Since degree of x plus degree of y is greater than or equal to n minus 1, it follows that there is some vertex w such that xw and yw are edges. Okay, so that's a bit of a leap. Why is this line that I just wrote true? That's something to think about. Since degree of x plus degree of y is greater than or equal to n minus 1, it must mean that they have some vertex in common, that their neighborhoods intersect each other. So why is this true? Let's look at this. So here's x, here's y. I know they're not adjacent, so that's a non-edge between them. And I know that x has some neighborhood right there, and y has some neighborhood. So there's n minus 2 other vertices in the graph. And I know that degree of x plus degree of y is at least n minus 1. So 1 more than the number of vertices here. By the pigeonhole principle, so this is really pigeonhole principle. By the pigeonhole principle, why don't I just write it out? By the pigeonhole, there is some vertex adjacent to both x and y. So how about that one? Right, there's n minus 1 edges coming into this set of n minus 2 vertices. And so there's one vertex in here which must have 2 edges coming to it. Well, they can't both be coming from the same vertex, otherwise it's not a graph. And then we have an edge to x and an edge to y. So this would be my w. So then x, w, y is an x, y path. In particular, x and y are connected, and therefore the graph is connected. So that's the idea. This really comes down to pigeonhole principle. Now, coming off of that corollary is a minimum degree minimum degree result. That is, if a graph of order n has minimum degree at least n minus 1 over 2, then G is connected. So how does this follow? Well, this actually follows immediately from the previous one. So let's say proof, let U and V be non-adjacent vertices. I'll show that their degree sum is at least n minus 1. Then degree of U plus degree of V. Well, the minimum degree is n minus 1 over 2. So in particular, degree of U is at least that, degree of V is at least that. And so this is greater than or equal to n minus 1 over 2 plus n minus 1 over 2, which is just n minus 1. So this non-adjacent degree sum is at least n minus 1 by theorem 2.3. G is connected. Now I do want to say something here. So that the corollary is not too hard to show, given the previous theorem. I do want to say something here about best possible theorems or bounds. That is sharpness of a bound. So the question becomes: can this degree sum be improved at all? That is, if degree of U plus degree of V is greater than or equal to n minus 2, is G necessarily connected? Or is there some graph where the non-adjacent degree sum is exactly n minus 2 and the graph is not connected? And that is the case. So degree U plus degree V greater than or equal to n minus 1 is best possible. So consider the graph G, which will be, so this will be order 2k. This will be k, so k vertices forming a complete graph. Another k vertices forming a complete graph. And notice here what the non-adjacent degree sum would be. So I have vertex here, U, and V. It looks like a couple of eyeballs. U and V. Degree of U is what? It's adjacent to every other vertex here, so that's k minus 1. Degree of V is also k minus 1 other vertices in this complete component. So degree of U plus degree of V is equal to 2k minus 2, so that's the order of the graph minus 2, but G is disconnected. So what this is saying is that this theorem cannot be improved. There's no stronger theorem than this about non-adjacent degree sums, that n minus 1 really is sort of the magic number here. As soon as the non-adjacent degree sum is at least n minus 1, I'm guaranteed to be connected, but there's some graph where this non-adjacent degree sum is n minus 2 that's disconnected. So that theorem cannot be improved without more information about the graph. So that's theorem 2.3 and corollary 2.4. So we have a sufficient condition to be connected that's based on non-adjacent degree sum. We have a sufficient condition for connectedness based on the minimum degree. And finally, what's another sort of condition along this line? That's just the total degree, the total number of edges in a graph. So that's what theorem 2.5 is saying, is that we need, this is a really rough one, right? We need the size to be at least n minus 1 choose 2 plus 1 edges, and then we'll be guaranteed that the graph is connected. So just a note on this first, if I form the graph G of order n, that is, let's say k n minus 1, so a complete graph of order n minus 1, and then just a vertex. So this would be, we could call this k n minus 1 plus v, plus some vertex v, right, a union of two graphs. Then the number of edges here is n minus 1 choose 2, and G is disconnected. But as soon as we have one more edge in here, n minus 1 choose 2 plus 1, we're necessarily connected. So again, this theorem is best possible. So let's prove, let's see, where are we at? Yeah, let's prove this one. So proof, why is this true? So, right, we can just verify this for n equals 3, 4, 2, 3, and 4. So assume, it's fine to assume n is at least 5. We're looking at a graph with an order at least 5, and let u and v be two vertices. G, we show there is a UV path. So again, if UV, if they're adjacent already, if UV is an edge, then we're done. We found a UV path. Also, let's see, what other case are we fine? So if G contains a vertex, W, such that U, W, and WV are edges, then what? Then we can do U, W, V is a UV path, and we're done. So we can assume that there is, there is no vertex adjacent to both U and W. No vertex adjacent to both U and V, to both U and V. In particular, the degree sum, degree of u plus degree of v, has to be less than or equal to n minus 2, right? We know if this non-adjacent degree sum is at least n minus 1, then they have to have a vertex in common, and so this is the most you could get away with. We know that their degree sum is at most n minus 2. Okay, so what we'll do here is remove u and v. So let g prime be g minus the two vertices u and v. So let's check on this. So g prime has order n minus 2, and how many edges? And so let's say and size m prime for the number of edges, which is, so we took away a bunch of edges when we formed g prime, so it was the number of edges in g minus degree of u minus degree of v. But now I have a bound on this degree of u plus degree of v, right? This is less than or equal to n minus 2, so when I subtract that, this is greater than or equal to m minus n minus 2. Now, by assumption, m is at least n minus 1 choose 2 plus 1. So this is at least n minus 1 choose 2 plus 1 minus n plus 2. So that is n minus 1 choose 2 minus n plus 3. And now how do we get a contradiction here? So actually, let me leave this as this minus n minus 2 plus 1, like that. I'm going to leave it like this. Now, if you happen to know some tricks with binomial coefficients, this is sort of immediate. What I want to say here is that n minus 1 choose 2 minus n minus 2 is equal to n minus 2 choose 2. So this is true for binomial coefficients. There's some kind of recursion here for binomial coefficients. And I guess I'll just show this. I'll show this just directly. So n minus 1 choose 2, right? This is n minus 1 times 1 less n minus 2 over 2 minus 2 n minus 2 over 2. Get a common denominator, and then I still have this plus 1. I'll combine these two fractions. So this is what? N minus 1 times n minus 2 minus 2 n minus 2 all over 2 plus 1. And now I can factor out this n minus 2 term. So this is what? N minus 2 times, what am I left with? N minus 1 minus 2, so n minus 3 all over 2. I still have the plus 1. And now here, this is n minus 2 choose 2. So this is n minus 2 choose 2 plus 1. Okay, great. Well, so what did that do for us? Well, in particular, I just found, right, this is the size of g prime, right? M prime is greater than or equal to this. So why is that a problem? Do you see the contradiction yet? Remember, M prime had order n minus 2. Or G prime has order n minus 2. So M prime, the most number of edges, would be the complete graph of order n minus 2. So M prime is less than or equal to n minus 2, choose 2. But we just showed it's greater than or equal to n minus 2, choose 2 plus 1. So this is a contradiction. That's a problem. And that proves it. So necessarily then G is connected. Okay, I think that's it for this video. And that's it for this section.